The way that we typically determine activation energy is to construct a plot of ln k versus 1 over t. And what we get from that plot is a linear relationship where the slope is equal to negative EA over R. So knowing the value of the slope and rearranging this equation, we can solve for the activation energy. We can do something similar if we are given 2 data points, and in that case we will construct a 2-point slope and then do the similar calculation to arrive at the activation energy. What I typically do with these types of calculations is I'll set up my own table of data just so I know how I'm keeping track of the calculations. So in this example, we are given a rate constant of 5.62 times 10 to the negative 2. I'll just put the units up here so I don't have to write them every time. And the second rate constant, 3.09 times 10 to the 1. We're given a temperature in Celsius for the first data point of 25, and then the second data point of 200. That's the original data. That's what we're provided in the problem. So we're then going to get information of ln k, temperature in Kelvin, and then 1 over temperature in Kelvin. 1 over temperature with units of inverse Kelvin. And then I can extract the ln k and 1 over t data to plug into the 2-point slope. So the first calculation is ln k for the first data point. And when we do that math, we end up with negative 2.879. Let me remind you about the sig figs for logs, and that is if we have 3 sig figs, then we need to end up with 3 decimal places. Calculating ln k for the second value will give us 3.431, also out to 3 decimal places because of the original 3 sig figs. Converting the temperature to Kelvin, just as a reminder, is degrees Celsius plus 273.15. That conversion is exact. So the sig figs are going to be based on whatever number of places you had for the original degrees Celsius. Now in both of our cases, our temperature is given to us out to the ones place. And so when we round, we will not have any decimal places remaining. So our 25 degrees converted to Kelvin will be 298, and our 200 degrees will be 473. Taking the inverse of each number, so now that's a division problem. We have 3 sig figs in each Kelvin temperature, and so we will keep 3 sig figs over here with the inverse. I recommend writing these out in decimal notation because when we go to the 2-point slope, you're going to have a subtraction, and you want to make sure that you're able to very clearly count the decimal places over there. So for our 1 over k for the first value, 0.00336, and for the second value, 0.00211. So for our 2-point slope, as I mentioned earlier, we need ln k and 1 over t. ln k is the y, 1 over t is the x, and those will be incorporated into our slope formula. So our slope formula, y2 minus y1 over x2 minus x1. Remember that slope has units. We'll incorporate those in just a little bit. So our y2, actually let me go back and just put arbitrary numbers to the experiments. It doesn't really matter which one you're calling 1, which one you're calling 2. You just want to make sure that you're keeping the data connected to the right to the right experiment, to the right trial. So this is how I will number my 1s and 2s. So Y2, 3.431 minus a negative 2.879 divided by 0.00211 minus 0.00336. We have two types of sig figs that we need to deal with. In our numerator, we have 3 decimal places for both values. So our numerator needs to keep 3 decimal places. In our denominator, we have 5 decimal places for each value, and we'll keep 5 decimal places over there. So doing the math, we end up with 6.310 in the numerator and negative 0.00125 in the denominator. Now I said that I was going to incorporate the units in a little bit. I didn't do that yet. In our numerator, the units will be Y units. ln k is unitless, so there's nothing for the numerator. The denominator has units of 1 over k, or inverse k. And so what I typically will do if I have inverse units in the denominator is I will just flip that to the top. Taking into account how many sig figs we have now, because although we had to keep track of decimal places in the first operations, we now have to look at the number of sig figs to do this final division. So our 3 decimal places at the top is 4 sig figs. We have 3 sig figs. So our final result is going to get rounded to 3 sig figs. So when we do the math, we end up with negative 5.05 times 10 to the 3, and those units are Kelvin. Now I know the units seem a little bit strange, but once we finish that calculation, because this is not EA, right? We have that one more step we need to do, then you'll see that the units work out. So finishing that up, our slope equals negative EA over R. When we rearrange that, we get EA equals negative slope times R. So now we're going to plug our values into that equation. So EA equals negative slope, which is a negative 5.05 times 10 to the 3 units of Kelvin, times R, 8.314 joules per Kelvin mole. Make sure you're including all of the units here, because this is one of the things I'll see students will just do the multiplication because that's not that difficult. But if you're not carefully keeping track of the units, it's easy to miss what the final units are of activation energy. So in this case, if we cancel Kelvin and stop here, we would be left with units of joules per mole, which is fine, except for the question asked for kilojoules. So we just need to do that final conversion. 1 kilojoule is equal to 1 times 10 to the 3 joules. Joules will cancel. We're going to keep track of our sig figs again. We have 3 from the slope. R is exact, and prefix conversions are always exact. We're almost done with this one. So when we get our final result, we will end up with 42.0 kilojoules. Kilojoules per mole.